Okay, so welcome everyone to this fourth session. This is the last session of this block, and we'll have a next round of talks in the autumn, probably starting in September. So to close this first block, it's really, really nice to have Christiane Klein, who's here in York, and she's going to be talking about the challenges of exploring quantum fields in rotating black holes. Thank you. Christiane, the floor is yours.
Thank you, Venuto, for this very nice introduction and for this opportunity to speak here today. As already mentioned, I will talk about the challenges of exploring quantum fields in rotating black holes, in particular, different properties of rotating black holes that make it difficult to construct states and study solutions of wave-like equations. And I hope you can all see my mouse. So let me start with a brief motivation. Why should we care about rotating black holes in particular? Well, first of all, because as far as we know, the black holes that we can observe in our universe as of today, for example, by looking at their shadows here for the black hole in the center of M87, or by observing the gravitational waves that are emitted by the merger of black holes, are rotating significantly. So both to interpret these observations properly and also to use them to test the theory of general relativity and probably theories beyond, we first need to have a good theoretical understanding of these kinds of objects. On the other hand, rotating black holes also provide us with a number of theoretical puzzles, some of which are still open today. And they range from purely GR questions, for example, the nonlinear stability of black holes, or in other words, if we look at the Einstein equations as an initial value problem by putting some initial data on a surface like this sigma here, that is close in some sense to a rotating black hole, do we asymptotically get back a rotating black hole, possibly with a different mass and angular momentum? And this is still an open question in pure general relativity, with some results now being there that say it's true for small angular momentum, but large angular momentum is still unknown. There are also problems that are very intimately linked with the presence of quantum matter, such as the question of black hole evaporation and what a consistent picture of that could look like. And of course, it has some relations to weak cosmic censorship, if we think about how does this black hole evaporation end, and also to information loss paradox. And we've had a very nice talk about this topic already in the series by Eric Curiel last time. There are also some puzzles that can be addressed both purely classical and with taking quantum effects into account. And one example, or two examples actually, are the strong cosmic censorship conjecture. So the question of if our maximal Cauchy development of solving initial data problem to get our space-time has a smooth future boundary, such as it has for rotating black holes, can we somehow prevent this non-unique extendability of the space-time and, in this sense, loss of determinism in pure general relativity? And there's a somewhat related question, namely, because the resolution of strong cosmic censorship is that these horizons turn into singularities, but singularities also mean that the physical theory breaks down. Is there another resolution of this without singularities, either by adding the proper quantum effects or maybe by amending the classical theory? So to put it briefly, there's a lot of things we can still learn about rotating black holes, and that we still want to learn about rotating black holes. And for this, for many aspects at least, we would also like to understand how quantum fields behave on these spacetimes. So to start, let me introduce spacetimes that actually describe rotating black holes in isolation. And these are the Kerr de Sitter spacetimes. So to define them, we first define this function delta r, which depends on two parameters. A is the angular momentum of the black hole per unit mass, and m is the black hole mass. And we will choose it such that the absolute value of a is smaller than m, in which case this polynomial has two roots in r, which we call r minus and r plus, and they are real and distinct. We then put the manifold to be just the real line times the interval r plus infinity times s squared, and we equip it with a Lorentzian metric of this form here. So the particular form is not all that important. What's important is that this is independent of both t and phi. Okay. However, we could also have chosen the interval r minus r plus instead and equipped it with the same metric. It's still a smooth metric on this region. And the big difference is now that delta r, of course, has the opposite sign. So in the sign convention that I use for this talk, which is minus plus plus plus, r is now a time-like coordinate. And so the diagram, Penrose diagram, looks like this. And this is the interior of the black hole. We could also have considered, of course, the interval 0 r minus or even minus infinity r minus. However, if rho squared goes to 0, which happens when r goes to 0 and cosine theta goes to 0, so on the equator at r equals 0, the Kretschmann scalar actually diverges like rho to the minus 6. So we have a curvature singularity. However, we could still consider this region by just taking out the r equals 0, theta equal pi halves, but we will not look at this region because it's causally vicious, meaning you can have closed time-like curves between any 2 points if you want. It is very nasty, and we will just ignore it for the time being. So what happens if you put in a positive cosmological constant? Well, this delta r changes a little bit. You get this additional factor here, which is proportional to the cosmological constant lambda. So now this is a fourth order in r, and we will choose lambda in a sufficiently small so that we have 3 distinct real positive roots and 1 negative root, which we will also forget about. And the additional positive root we get is this RC, the radius of the cosmological horizon, which scales roughly like 1 over square root lambda. So it goes to infinity when we set lambda to 0. We then take our manifold to be, for the moment, this one here. So we take the interval r plus rc, and we change the metric slightly by adding factors of chi and delta theta. However, you can convince yourself that these are bounded. This is actually a constant, and this is bounded. So they don't change too much about the metric, in fact. The biggest change is that now this here is not r going to infinity, but is in fact another horizon. And we can, again, also, we could have picked the interval r minus r plus, and this looks more or less exactly like in the Kerr case. But we also have an additional interval we can pick, which is rc and infinity, where now again delta r is negative, so r becomes a time-like coordinate, which increases to the future in this choice of time orientation. And this is now r going to infinity as a time-like surface in this Penrose diagram. So to construct what we consider the physical Curtis-Sitter spacetime, we now have to put these pieces, these blocks together. And one way to do this is to change the angle to the ingoing azimuthal angle by adding this integral here. The constant can be fixed in such a way that it's consistent, and going to the retarded time. So we add the tortoise coordinate r star to t, which is defined by this equation here. And again, once you integrate, you have to fix the coordinates in a way that it's consistent. Then you consider the manifold r in terms of v times the bigger interval r minus infinity times s squared. And when you look at the behavior of the metric in these new coordinates in the different blocks, it turns out you can actually smoothly extend it to all of this space-time. However, notice that while regions 1 and 2 look the same as we had before, region 3, when we embed the block into this bigger spacetime, actually comes out with the inverse time orientation. We can do something similar by just here and here changing plus to minus, and then basically doing the same thing. And again, when we embed the blocks that we constructed previously into this, now 3 comes out with the right time orientation, but 2 comes out with the opposite one. Now, we could just stick one copy of this and one copy of the previous one together to get the whole spacetime that we want. However, what we can't cover in this way are the bifurcation spheres of the event horizon and the cosmological horizon. And since we occasionally want to look at them, let's see how we can cover them. One way is to introduce Kruskal coordinates. We get one set of those for each horizon. So they are formed by just taking these coordinates u and v that we constructed before, and then exponentiating them with a factor of kappa, and kappa is the surface gravity of the corresponding horizon, which is proportional to the derivative of delta r, absolute value of the derivative of delta r at that horizon. And the signs here are chosen in each block so that large u and large v are always increasing towards the future. We then also introduce a new azimuthal coordinate that is now adapted to a particular horizon by just subtracting the angular velocity of the horizon, which is defined in this way, times t. And we can then, for the case of plus, look at the manifold r squared times s squared, and it turns out the metric that we started with in these new coordinates can actually be smoothly extended to this whole manifold. And if we embed our blocks into it, we get the two blocks 1 and 2 that we started with, plus 2 copies with the opposite time orientation. And we can also do something similar, of course, for C. Here we get this additional condition that UC times VC is smaller than 1, which is just related to the fact that for UC times VC going to 1, R as a function of U and V is going to infinity. So this line here is UC times VC going to 1. Okay, in theory, we could now also do the same for R minus, and then we could again stick them together by identifying the different blocks in them. And then we can do this multiple times if we want, and we can extend this ad infinitum if we wish to. And this is the so-called maximal analytic extension of Kerr or Kerr de Sitter. However, what we're really interested in here is what we consider the physical Kerr de Sitter spacetime, and that will be just these 3 regions here, one copy of 1, 2, and 3 each. Now, let me list a couple of properties of this spacetime before we study fields on it. First of all, you can show that it is a globally hyperbolic spacetime. That was first realized in the case of Kerr by an explicit construction by Gerard, Hefner, and Rochner, and then I extended it to non-vanishing cosmological constant by taking their construction and amending it to allow for a non-zero cosmological constant. Another property is that, as I mentioned, the metric that we started with didn't depend on t and phi, so our spacetime has 2 killing vector fields, and it is axis metric and locally stationary. What do I mean by locally stationary? Well, if we look at region 1, where t is a time function, then we can still find regions, the so-called ergo region, where the derivative of t, if we plug it into the metric, becomes positive. And that happens if we get close to the event horizon, which is the same as in Kerr, but it also, in fact, happens if we get close to the cosmological horizon. Now, we can get rid of this part, for example, by instead of considering dt, considering the killing vector field that generates the cosmological horizon, which would be dt plus the angular velocity of the cosmological horizon d phi. And then we find this is time-like just inside the cosmological horizon, but it still becomes space-like if we get too close to the event horizon. Similarly, if we look at the killing vector field that generates the event horizon, that one is time-like just outside the event horizon, but it becomes null at and space-like beyond the so-called speed of light surface, which is located somewhere at large or close to the cosmological horizon, and which still exists if we let lambda, so the cosmological constant, go to 0. That means even though we have a time-like killing vector field at each point in this region 1, there is no killing vector field that is globally time-like in region 1. And this is what I mean when I say it's locally stationary. Another interesting property that will come up is trapping, which also exists for other black holes. Namely, we can find null geodesics that do not eventually fall into the black hole or travel to infinity, but which instead remain trapped between some minimal and maximal radial coordinates, which are low bounded by r plus and upper bounded by rc. And in contrast to, for example, Schwarzschild, where this is the light ring, which is located at exactly one value of r, which is 3m, this is actually confined to some sub-region of region 1. Okay, so now that we have some idea what space-time we're dealing with, let's put some fields on it, and let's do a very, very simple one. Let's do Klein-Gordon fields. So the field we'll consider is a Klein-Gordon field, and we will give it a mass mu squared, which in the asymptotic de Sitter case actually doesn't do much harm. And in fact, from a differential equation point of view, has the same effect as introducing a non-minimal coupling to the curvature. Since our spacetime is globally hyperbolic, and this is a normally hyperbolic operator, thanks to works by Baer and Berginu-Pfäffle and previous works, we know that there are unique retarded and advanced Green operators for this operator K, and this will be very important when we want to quantize it. However, before we do that, let me talk about a slightly different aspect, namely solutions of this equation on Kerr de Sitter. It was shown in the 70s by Tchaikovsky that to solve this, you can do separation of variables, and this will completely separate. So if you do an ansatz for your solution of this form, where this is just a normalization constant, you have some explicit factors, and then you put in e to the I minus I omega t plus e to the I m phi times some constant of theta times some constant of r, then the whole equation reduces to an equation for this s omega lm of theta and an equation for this r omega lm of r. This combination of the e to the I m phi and the s omega lm of theta for the case of Kerr is given by the so-called spheroidal harmonics, which is a family of functions on the sphere, on the unit sphere, that form a complete basis for smooth functions thereon. And for the case of non-vanishing cosmological constant, you can generalize this notion of spheroidal harmonics slightly, and you can solve for these numerically. The equation for r omega lm can be rewritten by using this tortoise coordinate that we discussed a little bit earlier, and it turns out to have this relatively simple form where this is a potential that if you write it also in this tortoise coordinate, that, recall, goes from minus infinity to infinity on each of these blocks, is localized, so it decays exponentially in r star. While this last term here goes to a constant, again, exponentially in r star. So what we have for this radial part is a one-dimensional scattering problem with a localized potential, but different asymptotics. So in general, we would expect to find solutions that look like free waves. And so asymptotically, they should behave like this, where omega plus and omega c are just omega minus m times the angular velocity of the corresponding horizon. And these a, b, c, d are complex coefficients. And then, of course, there are corrections once we go away from the horizon. Now I want to talk about two particular sets of such modes. The first one are the so-called in-modes, where we set this a to 0, and then by choosing this normalization constant properly, we can set d to 1. Now, the scattering problem doesn't have a first-order derivative term, so the Wronskian for this equation is constant, which means that by comparing it at different ends, we can get a relation between these coefficients c and b. And if we set d to 1 and a to 0, then c is the reflection coefficient and b is the transmission coefficient. So usually we would expect them to sum up, their absolute values to sum up to 1. However, because of these different asymptotic frequencies, there is the possibility that their product is negative, or their derivative is negative. So in that case, the absolute value squared of c is bigger than 1. And this is what people refer to as superradiance, namely, you get out more than you have put in. The second thing I want to talk about are quasi-normal modes. For this, we set both a and d equal to 0. So we have actually one more condition, because renormalizing d is something we can do, but renormalizing it to 0 with a finite renormalization constant isn't. And it turns out that this is not possible anymore for all frequencies omega, but only for a discrete set of generally complex so-called quasi-normal frequencies. And they are very important because they're related to the so-called mode stability, namely the property that the spectral gap, or the minimum of minus the imaginary part of these quasi-normal modes, is strictly positive. Or in other words, that all the quasi-normal frequencies lie below the real line on the complex plane. Why is this important? Because especially in the case of asymptotic de Sitter, these quasi-normal modes play an important part in estimating the decay of solutions to the Klein-Gordon equation, as there are no polynomial tails in this case. And with a positive spectral gap, we have exponential decay of all these quasi-normal modes towards Cry+, and we have no exponentially growing or modes that stay constant. However, it's very, very tricky to show this on Kerr de Sitter, and it's actually still an open problem to show this for all Kerr de Sitter spacetimes. It has been shown by perturbative methods for very small angular momentum or very small cosmological constant by Peter Hinz, and there are some results that move towards it by, for example, Marco Salz and Rita Teixeira da Costa, but there is no general proof. The big problem here is exactly superradiance. Without superradiance, showing this mode stability is comparatively straightforward, but given that there is superradiance in the problem, it's very, very hard. The way it worked on Kerr is people found, in particular Bernd Whiting, found an integral transformation which transformed the equation for R omega Lm, which has superradiance, into one that doesn't, but has the same quasi-normal spectrum. And in this way, they were able to show that for Kerr, there is a positive spectral gap. But for Kerr de Sitter, no such integral transformation is known, and it's still an open problem. Okay, so now that we know a bit about the classical theory, let's quantize it. And the first part of the quantization is pretty straightforward, namely getting the algebra of observables. Here, let's just consider the algebra of smeared field operators. So we look at the free unital star algebra generated by these phi of f, where I have some test function and a unit element. And these phi of f are linear. They are Hermitian in the sense where this is complex conjugation, and this is the star operation of the algebra. They satisfy the Klein-Gordon equation in this weak sense, and their commutator is just the retarded minus advanced fundamental solution acting on H integrated against F, which will be expressed in this way. Okay, now to compute or to do anything with this theory, we also need states. And this is where the complication starts. So in general, states are linear maps from the algebra to the complex numbers, so from operators to expectation values. So they need to be normalized and they need to be positive. That is simple enough, but if we want to compute anything, we want to have them explicitly, and ideally, we also would like them to be nice and physical and well-motivated and adapted to the situation we want to look at. So there's a lot of things we would like to have. So one thing one can do to simplify things a little bit is to focus on quasi-free states. They have the big advantage that they're completely determined by their two-point function. So if we want to construct one, we just have to give a bidistribution, W, and then make sure that it's a bisolution to the Klein-Gordon equation, that its antisymmetric part agrees with I times the retarded minus advanced green operator, so that it agrees with the structure of the algebra, and that it's positive for the positivity of the state. And this will uniquely determine a quasi-free state. Another nice thing about quasi-free states is that if we now do the GNS reconstruction with such a state, so if we use it to get a Hilbert space representation for our algebra, the Hilbert space we end up with is a Fock space. So we get back to the structures we're used to. However, this condition, while giving us the nice class of states, is not the only condition we want. We would also like our states to be nice enough that we could, for example, do things like define the stress energy tensor, which isn't part of the algebra that I've just shown, but we can add it by doing renormalization. And we want to do it, renormalization, in a way that is local and covariant. And the original proposal by Kay and Wald, or the original definition for this condition, was then that for small geodesic separation, the two-point function of the state should look like the Minkowski vacuum in the sense that the singularity structure is essentially a curved spacetime generalization thereof and is locally and covariantly determined from the theory and the local geometry, while the state-dependent part is smooth. And in the later 90s, Radzikowski found that this can be rewritten in the language of microlocal analysis using the wavefront set of the two-point function. So the wavefront set of a distribution in general tells you not only where it ceases to be smooth, but also in which directions in Fourier space these non-smoothnesses lie. And the prime just means that if we have two-point function of these bidistributions, that we switch the sign in front of the second covector. So the microlocal spectrum condition that Radzikowski showed to be equivalent to this original idea by Kay and Wald, with some gaps being closed a couple of years ago by Walter Moretti, is that the wavefront set of the two-point function is such that x and y, for x, k, y, l being in the wavefront set, should lie on a null GD6 segment, to which k is cotangent at x, and l is the same as k parallel propagated along the null GD6 to y. So it's also cotangent to the null GD6, but at y. And k must be future directed. And with this, with a state that satisfies this property, we can then add weak polynomials to our algebra and define things like a renormalized stress energy tensor. So for a general space-time, this is about as good as we can get, but for rotating black holes, we still have some symmetries. So we might think, well, if we have some symmetries, maybe we can use this to find distinguished physical states. And so let's say we have one parameter group of isometries on some spacetime M. Then this generates a one parameter group of star algebra automorphisms on this smeared field algebra by basically just pushing the test function forward with the inverse. We can then define a state to be a ground state with respect to this isometry by saying that the function t being a real parameter to omega of a alpha tb is a bounded function. It's a complex valued function. And for all test functions that are supported on the negative half line, the integral of this function of t against the Fourier transform of f vanishes. And this has to hold for all elements a, b of the algebra. Similarly, we can define a beta KMS state by saying the same function has to be bounded. And now for all test functions, real value test functions, the integral of these functions against the Fourier transform of t is left invariant when we switch the arguments in the state and at the same time shift the argument of f to t plus I beta. And beta is the inverse temperature of the KMS state. Okay, so these are nice classes of states that are very physically motivated. This, for example, contains Gibbs states. So back to black holes, if our isometry belongs to a killing vector field phi, there are a couple go and no-go theorems. First of all, if the vector field V is everywhere time-like, then in fact all beta KMS states and all ground states with respect to this isometry, as well as all convex combinations thereof, are in fact Hadamard states, and this is due to some. However, a slightly older result by Kay and Wold for Kerr says that if V is the vector field that generates the horizon, then there is no Hadamard state that is invariant under the star automorphism alpha t on the algebra of this whole Kruskal domain. And in fact, all beta KMS and ground state have this invariance property. So there are no beta KMS states, there are no ground states with respect to this V on the whole Kruskal domain. And in a similar direction, if this vector field V is space-like at some point x0, then the microlocal spectrum condition is for any beta KMS state and any ground state with respect to this V is violated at x0, which is resolved by Pinamonti, Sanders, and Ferch. So because we only have local stationarity in the exterior, we cannot really hope to get too much. But there are some things we can do, and to find out what, let's go back to Schwarzschild and let's go back to the 70s, when shortly after Hawking's result on black hole evaporation, there was a lot of work on quantum fields on this particular spacetime. And there were a couple of states being considered that are very physically motivated. So the first one is the Boulware state, which is a ground state for the usual time translation in the exterior region. The disadvantage of the state is that it breaks down at the event horizon, but it has the nice property that close to infinity, so near r going to infinity, it looks very similar to the Minkowski vacuum indeed, and is often used as a reference state there. To cover the horizon, you can instead look at the Hartle-Hawking state, which is Hadamard in the whole Kruskal domain. And if we restrict to region 1, it is a KMS state with respect to time translations at the Hawking temperature beta equal to 8 pi m, where m is the mass of the Schwarzschild black hole. The disadvantage of this is that it is somewhat unphysical in the sense that you would expect, if you're very far away from the black hole, to have something that looks like the Minkowski vacuum or like the Boole state, which this doesn't, because this is a state that describes thermal equilibrium with a black hole. So to somehow do something in the middle between the two, there is the so-called Unruh state. In contrast to these two, it's not an equilibrium state. It is neither KMS nor is it a ground state. It is constructed explicitly so that at Scri minus, it looks like the Boole state, while at Scri plus, you have the thermal energy flux you would expect to get from black hole evaporation. And in this sense, it is constructed to capture the late time behavior you would expect in gravitational collapse. And this was actually checked in, I believe, curve of fermions by Heffman. And I would argue that out of these three, it's also the one that extends the most naturally to de Sitter without running into any no-go theorems that tell us that we can't extend it without at least losing some of the defining properties of the state. Okay, there are actually some results where these states have also rigorously been extended to other spacetime. Notably, the Hartle-Hawking state has been shown to be a well-defined, explicitly constructed Hadamard state in any spacetime with static and later on stationary bifurcate Killing horizons by Sanders and then Gerard, using Wick rotation methods. The Unruh state has first been explicitly constructed and shown to be Hadamard, explicitly, rigorously constructed and shown to be Hadamard on Schwarzschild by Da Piace, Moretti, and Pinamonti. And their proof was later extended to Schwarzschild de Sitter spacetimes and Reise-Nordström de Sitter spacetimes by Broom-Joras and Hollands-Watt and Zahn. There's also a Unruh state, which has been shown to be well-defined at Hadamard on Kerr, but instead of scalars, it's shown for massless-free fermions and for small angular momentum by Gerard, Heffner, and Rochner. The advantage of fermions is, on the one hand, your classical solution space is a pre-Hilbert space instead of a pre-symplectic space, which makes some things easier. And B, you don't have superradiance. But as we will see now, we can also construct the Unruh state on Kerr de Sitter, and that was work that I did now a few years ago. So it is a quasi-free state, so all we need to do is construct a two-point function. Since we want it to be a bisolution, a simple way to achieve this is by mapping this distribution to a functional or a bilinear form on the space of space-compact solutions to the Klein-Gordon equation by using the retarded minus advanced fundamental solution. And then from there, we can use a null boundary to bulk construction, where we use that we can embed the bulk algebra into an algebra on the boundary. So we can construct the state by defining it on the boundary and then pulling it back to the bulk. And this was first introduced independently by Hollands and Moretti, and then also extended by Gerard and Rochner using my partial differential operator calculus. On the boundary, which in our case is H plus and HC, so pieces of the past event and past cosmological horizon, we use the K-Wald two-point function, and the thing that we get looks something like this. So this piece is from the metric determinant. We have our test functions plugged into E. We restrict to the corresponding horizon, evaluate at the same angular coordinate and different null coordinates, and then we divide by this factor here. And this limit of epsilon going to 0 is to be taken last in a distributional sense. Okay. One can show that this actually gives a well-defined state. First, you need to show that this is actually a well-defined expression, because of course the traces of solutions are not compactly supported. In principle, you could have contributions all the way down to I minus. But as I already mentioned, in the asymptotic de Sitter case, that is dominated by the quasi-normal modes. And in fact, Hinz and Vajda showed that near square minus, you can estimate this in terms of some coordinate t, frac, that looks like minus u near the blue horizon and like minus v near the red horizon. This is exponentially decaying. And here we have the spectral gap. So as long as this is positive, this is more than sufficient to show well-definedness of this definition and also positivity and the proper commutative property in the same way as it is done on Schwarzschild by Dapiati, Moretti, and Pinamonti, by amending their proofs to account for the different structures that are present here, like having two horizons instead of a horizon and conformal infinity. We also want to show that it is Hadamard, of course, and there a central role is played by propagation of singularities, which goes back to Dijkstermat and Hermander. And this allows us to, instead of checking the microlocal spectrum condition on each point of the cotangent space of m times m separately, we can check it on a whole geodesic, null geodesic at a time. So we have to consider one point on the null geodesic, and whether or not that is in the wavefront set will tell us whether or not the whole geodesic is or isn't in the wavefront set. So we then look at the first group of geodesics first, which are the ones that end at one of the horizons, so that we can use our definition. And in fact, combining this definition to do some direct computation with a number of cutoff functions tailored to the point that we want to look at, and using the decay that we have to deal with the remainder terms that we have cut out, we can check the Hadamard property. And this is, in a sense, very similar to what was already done in the works by Hollands and Moretti. The big difference is, of course, that we have square minus, while they were working on cones, where you have the tip of a cone. And also, we had to find some new ways to get to implement this decay to get rid of these remainder terms. Now, what remains to do to show the Hadamard property in full is to check the microlocal spectrum condition for path-trapped geodesics, so the ones that end not here or there, but at I minus. So for this, we want to use that while our state at full is not a KMS state, the two parts that it's made of are separately satisfy the KMS condition, but with respect to the different killing vector fields, namely the one generating the corresponding horizon, and also with respect to different temperatures. And this allows us to, for the two parts separately, apply the proof for passive states by Salmon and Ferch, a fact that was first realized by Dapiati, Moretti, and Pinamonti when they worked on the Unruh state for Kerr. However, the difference is that in the, not Kerr, Schwarzschild. The difference to the Schwarzschild case is there, of course, both parts are, one part is KMS and one part is ground state, but with respect to the same killing vector field, and this killing vector field is time-like in all of region 1, while we have them becoming space-like at points. So this really only works when both of them are time-like. Luckily, in their work on Kerr, no, really Kerr, Gerard, Hefner, and Rochner realized that if you take A to be sufficiently small, you can find a region where both of them are time-like that covers all path-trapped null geodesics at some point. So they all go into this region at some point. And you can extend this by analyzing the null geodesics to the case where lambda is non-zero, but still sufficiently small. What does sufficiently small mean here? Well, you can check this numerically. So this is the whole sub-extreme parameter region for A and lambda over 3, with M being set to 1. And this green region is an approximation of where we have mode stability results, well, this blue region is an approximation of where we can find a region so that both of these are time-like and all past trapped null GD6 enter the region where both of these are time-like. Okay, so we have a state that on a big chunk, well, big part of small chunk of our space-time gives us a well-defined Hadamard state. But this part here is actually parametrically quite interesting. So can we do something to extend our results there? And that is indeed the case. And to show that, let us go to Kerr, to the massless free fermions on Kerr. We don't need to know really anything about the theory. What we need to know is that, again, we have this Unruh state being Hadamard result for small a. And now, how does the smallness of a enter? It enters only in the proof of the Hadamard property. So the construction of the state goes through for any a that is smaller than m. And in the proof of the Hadamard property, it only enters in dealing with the microlocal spectrum conditions for the past trapped geodesics, the same as on the previous slides. And it turns out that both in the proof of on the previous slide, as well as in the one on Kerr, demanding that both the killing vector fields are time-like in a certain region is actually more than you need, because what you're really interested in is only a very specific subset of the cotangent space, namely the past trapped geodesics. And you have more information on them than that they are null. And that actually helps you, because by analyzing the past trapped set closer, you can show the following on Kerr. So if you have any element of the cotangent space of the Kerr spacetime that specifies a null GD6, so K is null, that does not reach H plus or scry minus and instead gets stuck and ends up at I minus, then if the contraction of K with either the killing field generating the event horizon or the contraction of K with dt is positive, K must be future directed. And this actually is a sufficient condition to show that the Hadamard property then holds for all a smaller than m. Because what you get out of either this Saman-Ferch passive state proof or out of the way the proof works in Gerard, Hefner, and Bruckner is that the wavefront set is restricted to such covectors that satisfy one of these two conditions. And if that is enough to show future directed, then you're done. And because this is purely geometrical, and because by a little more work, because of higher order polynomials, you can also extend this to Kerr de Sitter, this means we can also extend the proof of the Hadamard property for the Unruh state on Kerr de Sitter to all sub-extreme Kerr de Sitter spacetimes, still with a limit on the cosmological constant that we can have. But physically, I think this is the more reasonable limit, because the cosmological constant we want is very small anyway, but the rotation might be very large. Okay, how does this work very roughly? So the trapped geodesics are in region 1, so we go there. We go back to the very first coordinates we started with, the so-called Boyle-Lindquist coordinates. And then in these coordinates, we find an expression for what it means for a null covector to be part of future directed by basically getting these kinds of estimates. We combine them with a parametrization of the trapped set for the spacetime, which is due to Dyatlov. And then using this combination, we can show that there are no covectors in the trapped set that have negative T component, but their contraction with the generator of the horizon is positive. And now we only have to combine the relation between completely trapped UD6 and past trapped UD6 to show the final result that we want. And with this, we have a well-defined, very physically motivated state that is Hadamard that we can use to do things. So let me finish by very briefly giving you a rundown of what can you do with things. So, for example, as I already mentioned, the question of extendability of this space-time. You have this smooth inner horizon, and theoretically you can extend your space-time, for example, by analytically extending it, but this extension is non-unique from the perspective of an initial value problem. And the strong cosmic censorship conjecture says that, well, this extension is sort of a special case, because if you perturb your initial data a little bit, you get a singularity here. And you can look at this also by adding quantum perturbations to your initial data, so by adding a quantum field to your spacetime. And then it turns out that in certain Rice-Nordström de Sitter spacetimes, where classical fields only give you a relatively weak singularity here, of the very weak divergence of the stress energy tensor, the leading divergence of the quantum stress energy tensor is not only stronger than the classical results, but it's in particular independent of the choice of Hadamard states you made. So it has some genericity, and that was shown by Hollandswald and Zahn. And later, in a work with Peter Hinz, we showed that this does not only extend to all of Rice-Nordström de Sitter, but also to Kerr de Sitter, assuming that you have a positive spectral gap. So again, the spectral gap comes in here. And you can also extend it to more general observables that are quadratic in your field, and D1 and D2 are just any smooth derivative operators. And then what you can show is that the expectation value of the renormalized observable, so you have to renormalize in a local and covariant way by point splitting. As you approach the inner horizon, where v is 0, has a leading term which goes like v to the minus j, where j is the number of v derivatives in d1 plus d2, and a subleading state-dependent term where how subleading it is really depends on the spectral gap. Well, and now you can try to numerically compute these leading terms at the inner horizon. So here, for example, we have used the Unruh state to compute the leading divergence of the leading component of the stress energy tensor, and we see A, it's non-zero, and B, the features that we find are very similar to the ones you find on Kerr or Rice-Nordström de Sitter in similar numerical computations. So this is done on the pole. We also looked at other components of the stress energy tensor, where you know that the leading divergence is, in this case, linear. And here that's as a function of the cosine theta, so it's mapped over the inner horizon and for different values of the black hole angular momentum. And the key takeaway here is if you integrate this over cosine theta, this is all positive, which indicates that the angular momentum tends to decrease due to quantum effects. Another fun thing you can do at the inner horizon with these numerics is you can look at the correlations of the stress energy tensor components. So here, for example, the leading component and the correlation between the poles normalized to the expectation value squared. And what we see is that apart from where the normalized expectation, the expectation value vanishes, this is roughly of order 1. So there are very strong correlations between the poles, so over very long distances in this case. And this means there is another way in which this semi-classical approximation breaks down, apart from the whole fact that the geometry might become singular and that the quantum effects become singular and very, very strong. No, even before that, we have these long-range correlations, which mean that just plugging in the expectation value into the semi-classical equation is not a good representation of what is going on anymore. However, if we look at a toy model for cranking up the mass, because that is very hard to do numerically, which is looking at a charged black hole and cranking up the charge of a charged scalar field, we see that if we increase the charge, these initially long-range correlations start to die away. So it seems that if we draw this analogy, if we were to increase the mass in this case, that these long-range correlations might also become suppressed. However, we have massless particles, so we can't get rid of them entirely, it seems. Okay, so this is about what I wanted to tell you. So I hope I have convinced you that rotating black holes have a number of properties. Namely, they are only locally stationary in the exterior. There's trapping and there's superradiance that cause all sorts of challenges for constructing physically motivated, distinguished states with which we can compute quantum effects. There's a number of no-go theorems for ground and K-mass states in rotating black holes because, in particular, of this local stationarity property. However, we have shown that the Unruh state on Curtis Sitter is a well-defined Hadamard state, which has at least a number of properties that we would like from it. And we can use it to compute quantum effects, for example, at the inner horizon, to learn more about what quantum effects can tell us about the interior of black holes, and maybe in the future about black hole evaporation and other questions. With this, I would like to thank you and for your attention.
Thanks a lot, Christiane, for a very brilliant talk. Okay, I think that we can open the question session. So if you have some questions for Christiane, please go ahead by chat or on live, as you prefer. There is Dan with the question, sorry.
Hi, Christiane. Thanks for the talk.
You're very quiet.
Oh, is this better? Good, sorry. So you've talked about construction of Unruh state for scalars and for fermions. Do you expect any further difficulties when you consider higher spin fields, electromagnetism, Procca field?
Well,
or do you think
there are the typical difficulties, let's say.
Mm-hmm.
So, of course, for spin 1, you have gauge freedom that you have to deal with. And then there's always the difficulty of getting it positive and Hadamard,
Mm-hmm.
which sometimes seem to be a bit of a at odds with each other.
Mm-hmm.
And the same would, I think, go for spin 2, where the gauge thing is even harder. I don't know why you would want higher spin fermions. So I don't know how it would look there. Procca might be a bit easier than massless spin 1. So I think Procca might be doable. The question there is, this whole thing relies a lot on having a good classical theory, like good decay estimates.
Mm-hmm.
So the question would be, are there good decay estimates for Procca? If there are, and I think Procca might probably be the easiest other one once you have established the theory.
Thank you.
Okay, great. There is another question by Gosh, I guess. So.
Hello.
Hello. Hello.
Can you hear me? Yeah.
Oh, yes, we can.
Yeah, sure. Ma'am, excellent talk. I just have two quick questions. One is very basic because I am not very familiar with Carr de Sitter spacetime. That's why what I am asking. So you talked about when you are doing the construction about the Penrose diagram, you talked about the bifurcation sphere of that. I mean, like the when. So I was just wondering that for curved spacetime, when we do the Penrose diagram, we understand the bifurcation surface. I mean, that would be the wedge. I mean, where the null geodesics, the vanishes, right? But in the curved de Sitter, you have quite a few regions. Like, I mean, you have 3 regions. So I'm just asking that, is the bifurcation sphere is unique, or like there are 3 different wedges I can see? So that's what I was just first asking, that whether the bifurcation sphere for curved de Sitter space is unique or not, because I can see 3 different wedges. So that's what, when in the early time you defined.
So there are, in fact, 3 different bifurcation spheres. So each horizon has a unique bifurcation sphere. So the event horizon has its own bifurcation sphere, the cosmological horizon has its own bifurcation sphere, and the inner horizon has its own bifurcation sphere. And these are by the corresponding generating killing field vanishing.
But is it not a problem, because we need the bifurcation sphere to say calculate the world entropy, or what I know, I mean, to get it 0. So if there are 3 different bifurcating sphere, why do you put the, say, entropy or any other, like even the classical entropy to be 0, right? I mean, like we need the bifurcation sphere to put the integral to be 0 or something. I mean, it seems like unique bifurcation sphere is always preferable, right?
Well,
is that a problem? I mean, like in the ground state determining like what?
I mean,
so maybe in calculation it doesn't, but
there is no ground state, right? That was the whole point of the talk. You don't have a ground state on Kerr de Sitter, or not even on Kerr.
Oh, I see.
The best you can hope for is, in some sense, something that emulates a ground state where you want it to. And that is Hadamard, and that is quasi-free, and maybe has some other properties that you want. But you cannot find a ground state, because you don't have a globally time-like killing field. They all become space-like somewhere.
Oh, okay. Oh, okay. So, okay, actually, I probably misunderstood, because when you are talking about the 2-point correlator and other, I thought that, I mean, you had a well-defined ground state. So that is not the case. Okay. And second question is a little naive, but I could not resist asking, is that, let's say I understand that you did, like mathematically rigorous, you can find a lot of result in the Schwarzschild. I'm just asking that from a very phenomenological point of view. Let's say I take a Kerr solution in Barr-Linguist coordinate with the lambda term itself, and let's say I for rotating one, I mean the casual rotating, for static one, say Schwarzschild, I know the states exactly. Like, I mean, I know all the quasi-normal modes, or even the quantum field theory, all the A daggers, etc. So I'm asking that, just like slow rotating case, we can go to some lens threading effect by just giving a local rotation. So if I do for those states, I mean, some kind of, let's say, Bogoliubov transformation or some kind of like this, can we recover those KMS temperatures, or this is like inherently something which you have to do exactly? Like, how should I say it? Like, if you try to take like A tends to 0 and A tends to 0 and M tends to 0 limit, etc., this KMS state doesn't have a well-defined limit. So is it clear? Like, I'm asking that from static solution, if I want to go to the slow rotating situation, like to how we get the lens threading effect, can I use some Bogoliubov transformation to get those states, or is it something like inherently mathematical, like the very fact that Hadamard states are completely defined Hilbert space and one cannot be getting other by taking the limit? So this is just a casual question I was wondering. Because at the end of the day, I was wondering that whether I can beat it down to like the normal Schwarzschild, or like a Schwarzschild de Sitter, etc., to check that, I mean, whether the rotating limit actually vanishes or not. I mean, just like the Hawking radiation. I mean, even without the rotation, there is still radiation, right? So I was just wondering about that. Sure.
So the thing with limits in this setup, especially limits like A going to 0, and also lambda going to 0, is for some things they work, for some things they don't. Because, for example, take the case of lambda going to 0, it really changes the singularity structure of your partial differential of your differential equation when you do the separations. So you really get something different. It also vastly changes the asymptotic behavior you have. So between lambda being 0, where you have polynomial tails, and lambda being non-zero, where you have these exponential decays, you have very, very different behavior. So I wouldn't expect that things would automatically carry over naively from the a = 0 limit, because there might be other things that switch its nature really, really upon putting lambda non-zero.
Oh, yeah. Actually, the Cauchy horizon for de Sitter is very different than the Cauchy horizon for like Schwarzschild. I mean, yeah, the asymptotic structure also might play a role. Okay, thank you very much, ma'am. A really nice talk. Thank you.
Okay. Are there any other questions from the audience for Christiane? Maybe from the chat? Okay. Silvia. Okay, I don't think so. So I think we can thank Christiane again for the very nice talk. And I think that we can close the meeting. And I mean, as Benito said, this was the last talk of this